Thank you very much. Since it's the last presentation here, I try to make it nice and easy to follow. I will add some historical and personal notes and give some outlook. In fact, it's after 5 months, 5.5 months in France, I have the feeling I might be able to give a talk in French, but since part of the audience would then be excluded, I'm still staying with English. But I mean, my French has improved. Okay, so the first thing is a little bit of statistics. Preparing this event, I was looking up, and I thought it's nice to share it in a few minutes. If you look up in the mathematical genealogy and you look for PhD theses which have wavelets in the keyword, and I was looking on let is appearing but much less, then you find, I found 500, and meanwhile it's 508 PhD theses having this word in the title, which is quite an impressive number. In Central Blood of Mathematics I found 8,200 papers on wavelets and 121 books. If you sample it, I made the full statistics, but on one page I can show only this list. Then you see it was starting, of course, in the 90s with impressive numbers, constantly high in the 2000 years, slowly getting lower, but of course 2014 is not complete maybe by now, but I think it's clearly also decaying, which I think is understandable if you see that the people go on to compressed sensing and other interesting topics. I also found it quite interesting to sort the list of PhD topics having wavelets in the title by the years. Actually, I would suggest at least to the French community to check the onlet, because I found a couple of items, there are not so many, where there is no university, no affiliation. I think most of those PhD theses will be written under the guidance of people who are here or who know other people, so maybe you check it. And it was quite interesting to see Stefan Mallat really seemed to was the first one according to the mathematical genealogy, and other names that you may know in this list. So I just wanted to share this information with you. Now, next statement is there was life before wavelets. So I grew up in the world of abstract harmonic analysis, and I always have to mention Hans Reiter, who was my advisor. He viewed himself as a student of Andrew Weil, also not in a strictly formal sense, but he disliked the concept of harmonic analysis, abstract harmonic analysis, I mean the word, not the concept, the word, as it was used, for example, by Edwin Hewitt and others, where they say abstract harmonic analysis means taking results from the case of the real line and transferring it into the world of locally compact abelian groups. I think Reiter was always saying, well, no, you start with a group, and whether it's a continuous, in an engineering terminology now, a continuous or discrete group, a compact or non-compact group, periodic signals, non-periodic signals, there's always some Fourier transform expressed by the dual thing. So for me, when I think about time frequency analysis, what do you need? You need the group and the translations, and the dual group and the multiplications. And of course, then you have, if you want, the Heisenberg group, and the whole story can start. My original interest, and still, and that's what I came really very much back in this semester, is in function spaces. So I'm obsessed in understanding construction principles, not so much in the individual function spaces, but kind of why are people using function spaces? Well, in order to collect things, I mean, you should not do things individual, this function and this function and this function, repeat the argument. You're starting to think in terms of they're all members of function spaces. So you say, what are good function spaces? Very recently I finished an article which is entitled Choosing Function Spaces in Harmonic Analysis, and I will come back to this in the outlook. Essentially, we have a lot of function spaces, but we need now more information how to use them, where to use them, at which context or so. So clearly I was very much influenced by the work of the interpolation people, Hans Triebel and Jacques Petre. So trying to do function spaces on locally compact abelian groups and studying a little bit, not so, I was not focused on Siegel algebras. I was running into the problem when you do multiplier problems for Siegel algebras, very often you can say more if they have a multiplicative structure. So at the end, I ended up with character invariant Siegel algebras, which means you have Siegel algebras which are, by definition, translation invariant with isometric translation, homogeneous Banach spaces, but they're also isometric under the frequency shifts. Well, nowadays I would say I was restricting my focusing on the family of time frequency shift invariant Siegel algebras. Now there's a subclass of a larger class, but if the small guys have a minimal element, that's actually the minimal element in the whole space. And so I was discovering this zero Siegel algebra. The zero is just for the smallest in the family. And I presented it in the February of '79, and the paper came out in '81. And essentially, if you look it up now, it says this is a good space for many purposes. And Hans Reiter really was working with the Schwarz-Brühal space. He was suffering very much in the literal sense. I mean, you know the Schwarz space is very good. You do it on groups. You have to do group theory, structure theory, or so. At the end, you get the results. And I felt a little bit unfair when he was asking me, can you do it with a zero? And I was saying, well, I have to look at it. And the next day I told him, yes, it's a short proof. And so we're in a situation where for a larger space, you can give easier proofs. And until now, I think this is the general framework. Franz Lewis had a lot of other examples where replacing even on the Euclidean case, so when engineers want to have distribution theory, they don't need necessarily the Schwarz space, but they need a sufficiently large environment so that they can have Dirac comps, the Fourier transform of Dirac comps, validity of Poisson formula. For us, of course, S0 turned out to be quite relevant for time frequency analysis. When have you good convergence of the short-time Fourier transform or Gabor sums and so on? But this was really at the time before I was doing this, and because one of the descriptions of this particular Siegel algebra was you go to the Fourier transform domain, you cut the Fourier spectrum into pieces, and these, meanwhile, quite popular bupus, which are kind of the uniform versions of dyadic partitions. You can do them on any group. Even if you have not a lattice structure, you can still control the size and say, band-limited functions, even if they are not strictly band-limit, but the diameter is good, you can use Shannon's theorem, you move it to the center. So if a Banach space contains functions which have a certain diameter of the spectrum, and then you make an algebra, then you can have everything quite fine. Now, the good thing, and that was the original, one of the original purposes, is S0 can be defined for any locally compact abelian group. It's really interesting for the Euclidean case, but if you take the torus, well, it's the Fourier algebra, and the whole torus is just one element, so it's just A of t. So I think it's really the right generalization of A of t. And if you take S0 of the integers, it's just L1 of Z. Then you see immediately they are corresponding to each other under the Fourier transform, and that's the general truth. If you go from the group to the dual group, S0 goes to S0. Many other important properties like tensor product property, which allows to prove a kernel theorem, can be proven. And so it's really something we were using all the day now. About this time, so I had these function spaces. I was meeting Franz Lavac from the Technical University, already interested in getting into contact with the applied side. And he was telling me two things. He himself was working on the pseudo-Wigner, and I told him about my atomic characterization of the zero space, and he said, well, Gabor said you don't need all the time frequency shifts, you need only the ones from the lattice. And in addition, how do you compute the coefficients? And these were very challenging things, and so I slowly understand to make the connection between the function spaces I had with the applied problems, with the questions of Gabor, reading a lot of literature in this direction, and also to understand the connection with the Heisenberg group. So this was... now, in this time, I was also a librarian, and one of the preprints that came over the table, so to say, because I was catalogizing all the reviews, was this very interesting paper. It was immediately catching my attention about functions decomposition in constant shape, and I was seeing the group theories there, and I'm interested in function spaces, so that's exactly what I have to study. And very soon I was making contact with Alex. I was coming to Marseille, and a little bit later also then Charlie was starting a project with me where we tried to work on this. So just to mention the early papers of Grossman, Meyer, especially this minimality was clear. He was talking about the minimality situation with the AX plus B group. I had already the minimal space. Of course, at that time, modulation spaces were not known because my paper was not accepted and I was not following up very much. So I had a kind of a secret analog theory to Wavelet theory, except I didn't have orthogonal basis. We know now, of course, because of Balian law. But that forced me into working with non-orthogonal systems, that forced me to work with frames, to think about frames and so on. So these papers were quite crucial. And Charlie Gröchenik and I myself were doing this work. Yes, I had also had this atomic decomposition, just to make it short. As you can see in this painless paper that everybody knows of Ingrid, Alex, and Yves, there was a parallel world. So Gabor theory and Wavelet theory were more or less at equal footing. And then I think it was due to the existence of orthogonal bases, things were changing very much. And I remember also the discussion with Yves Meyer. He said function spaces are here to describe operators. Now, what he was having in mind was very clearly Calderon-Sigmund operators. I had heard talks of him in LS Corial. So now we have the right function space. I mean, we have the classical function spaces, but we have the right expansion to express the sparsity. So that was kind of the concept. In the time frequency world, we had to wait a little bit, and I don't want to talk about this much, but it turned out the modulation spaces are the right spaces for slowly varying channels. So we are meanwhile in the situation of even having patents on mobile communications, which are based on the sparsity of the representation in the Gabor basis. So I think that's a very interesting story. So maybe I just mention in 2-3 lines in the blackboard, what is the idea of Coorbit spaces, that somebody is giving me a nice locally compact, not abelian group, a non-abelian group, a representation which is having some extra properties, I would say integrable and irreducible, and if G is something like a reference building block atom or so, and X is an element on the group, I would describe the behavior of F by analysis, meaning correlation against these building blocks. So this kind of generalized Fourier transform is the study, and whereas, and I think it's analog to the theory of the K-functional of Jacques Petre, where you say, I'm living in L1 plus infinity, but then I want to see how different equivalent norms behave when I change a parameter, and the parameter is the real parameter positive t, that I can get a lot of spaces. I can get LP spaces, even Lorentz spaces or so. So more generally, you can do something which is in an arbitrary measure space or so. Now, I was saying, well, this is nice. This is not just an arbitrary space where you have a Haar measure on the group, but in the topology, but you also have some invariance properties, so you can define this elements F from, well, a sufficiently big space. You would think of distributions of all analytic functions or so, such that this voice transform is in some function space, and there is where my specialty came in. I didn't like to say it has to be an LP space, a mixed norm LP space, a Lorentz space, an Orlin space or so. All you need is what I call solidity, so it has to be a Banach lattice, and it has to be translation invariant. And that is enough to guarantee that with a very natural norm, you measure the y norm of this here is giving you a function space norm. So the norm is just go to the transform domain and measure it in the y space.
Could you define solidity, please?
So, sorry, this is the lattice property. So if you have f in y and g is a function which is a little bit smaller in terms of absolute values, then you would expect that g is in the space and has a norm which is smaller than this one. So the typical property of LP spaces or all these function spaces. So you should not say, let's say, bounded variation, because you have a plateau function with low variation and a small one which has a lot of variation. So, but otherwise, it's a very general concept. And why is this helpful, or how do you need it? Well, we have this very nice property that Vg of pi of f, or pi x0 of f, at least in absolute values, is typically a translation of the VGF. So you have an intertwining property applying an action of the group. So in wavelet theory, you would say affine transformation of the function is visible in the scalogram by a translation in the sense of the x plus b group. And of course, if I want to replace the window G by a translated version, I can also control it. If I have a linear combination, even if infinite sum, I can control it. And that is the crucial property that allows us to show the independence of the atom. So these function spaces would not be meaningful if they would depend on the choice of the G. And there are all kinds of conditions that help you to control when is a function G okay. Very modern development is by Hartmut Für and his student Felix Feuchtländer. They are studying the connections to representation theory, and they say, well, it's nice that you have an abstract condition, but how can you make it concrete? How can one verify it in concrete circumstances? And very often you find out it's moment conditions, it's decay conditions, it's maybe some cancellation conditions, and it depends very much on the context. Now, the main point at the time when we were doing this was to unify wavelet theory, time frequency analysis in the sense of the Heisenberg group, and these function spaces that you have on the unit ball of Moebius invariant functions on the unit disk, where the Petre, Arasi, and so had a lot of papers. Now, it was already the hope at this time that one could later on find more general groups. But there was a gap, and I think it was because we were going too much, or we were focusing more on Gabor analysis. We tried to do numerical algorithms to understand Gabor multipliers, all these things. So to say, to develop a good understanding in a concrete case, so that we ourselves did not care too much about other groups. But meanwhile, and that's in the last 10 years again, very fashionable, that people say, well, what are other groups which act here? And I'm quite sure, I mean, that people in theoretical physics know a lot of concrete groups that can be used. Some of them are not have not square integrable representations. Then one has to either quotient out or make fibers or so. So I think there is still a lot to be done. Margit Papp, for example, was using the Blaschke group to have something which is not far away from wavelet theory, but still one has to do this job. And yes, and the main point is, in each of these situations, if you're in a group, you know what density is. So somebody is giving you a small neighborhood of the identity, and you're taking points and you're covering the group with little balls. And so the theory was giving us as a main result that there's an atomic representation. So you're giving me the space Y and the representation and of course the group. And then I would say, yes, I can fabricate a mapping into the coefficient set, so whatever dense subset xi you give me, such that with the building blocks of the form p pi xi of g, I can fabricate every element, and this representation is convergent in the appropriate space. You give me a function from a Sobolev space, and it will be convergent in the corresponding norm. So that's the main point. And there is a sequence space. And the sequence space, so the main point is maybe I have a coefficient mapping, so that f goes to f psi I, And usually I describe it as, you would say, okay, it's going from H into the range of the coefficient mapping, which is inside L2. And now I find it very important to have a diagram of this form. Why? Because at the definition of frame says, here you have norm equivalence. You can measure the signal in the Hilbert space, or you can take the coefficients and measure it in the L2 sense, they're equivalent norms. And I think that's a misleading thing when you go to Banach spaces. You think, okay, you replace this by Banach space, and you have an appropriate sequence space. Well, then I say, okay, you have Fourier series. L2 goes to L2. I take LP, p equals 5, and say I have a Banach frame because there's a norm equivalence between the L5 norm and the norm of the Fourier coefficients if I take the norm from the other space. So you're doing some thresholding, you're doing anything that people in wavelet theory would do, or you have noise on your data, you are not coming back. So I think it's very important that you have the solidity at this level, so you have a sequence space, and then of course it's important that you have this projection. Now the next thing that I learned from the whole situation was, and usually I formulate it, well, even Hilbert spaces are human beings and like to come in families. So in most of the time we have L2 of R, we have families around these spaces, and the whole diagram should go with families. So families are important. Pardon? Yeah, and of course the family depends on the environment. If you're talking about X plus B group, you are back to the traditional spaces that are Tribble, Sorkin, Biesov, and such spaces. When you take Gabor, they don't fit. Well, it's not surprising because classical smoothness in terms of differentiability does not go well with weighted LQ conditions. They're nicely embedded one into the other, but if you say, well, I don't care about the connection between classical differentiability, and if you think long enough, you say, well, what if the world had started with scale space and frequency was discovered later? We would say scale is such a natural thing, but we can describe it also with this strange new concept of frequency. Just think of yourself of this possibility. We have spent centuries almost as a community with frequency, and we think that's the only and most natural thing. So we have the classical function spaces, but I think one could have done modulation spaces as I'm using them already at the beginning of the last century, because as soon as you have Fourier series, you can cut the function into pieces and take Fourier series expansion of the pieces. So it's just a matter of history. Now, the lesson that I want to mention is, when you have frames, and then I'm using, mentioning, so we are discussing for a small moment the concept of Banach frames. One should not think of a Banach frame being something about norm equivalence. A Banach frame is an embedding of a Banach space into a closed, complemented subspace, so that when you are having something which is modified in the range, you are still in this space. I also think that Charlie should have added, Charlie Gröchenig has given a formal definition, but I think he didn't. I would prefer to see in the definition that this space should be solid, so you can manipulate with it, and then you can come back. Secondly, it doesn't make, for me, any sense to say I have one Banach space and one Banach frame, but it makes sense to have this whole family. Later on, we were, and just mention it, we were doing, as a sidestep of this Coorbit theory, we were doing irregular sampling theory. It was a very long sidestep and a very fruitful one. But there, I think it's also the good, easy way to explain the situation. Somebody says, there's Shannon's theorem. Okay, then you generalize it. And there's a very big difference whether you can say, well, tell me, you can take any weighted LP space, I can prove a Shannon's theorem. And imagine the situation, a user is coming, bringing you some data, and you say, well, I can reconstruct it, but please tell me, is it in a weighted LP space with p equals 5 and polynomial weight of this order? No. You would like to have exactly the kind of situation that you have here. You would like to have a machinery which maybe is only good for a particular not too broad family of spaces. So you might not be able to allow super exponential growth or decay, But if you say, well, I want to discuss polynomial growth up to order 10 and decay of order 10, why? We have learned in wavelet theory you cannot characterize Beer subspaces of high order if your wavelet is not appropriate for it. But when you have a good wavelet, you have always a range of spaces. So I think that's one of the things that I wanted to mention. So yeah, so these are the papers in 88, 89. These papers were introduced. Now, yeah, maybe I leave this here. I would like to mention 2-3 more things. So I have already said Banach frames are an important point. The opposite, so to say, Banach frames are like generating systems in Banach spaces, stable generating systems. Now the opposite in linear algebra, you teach linear independent sets. Well, these are Riesz spaces, or modern terminology, Riesz basic sequences. And there you can have the same situation. That's, for me, the situation of spline spaces. You have first splines and you have Riesz spaces. But then you want to have weighted coefficient spaces, and you're getting cubic splines in weighted LP spaces. So this is absolutely the same. I was talking about Banach, about families. So because I realized when I explain these things to engineers or so, because I think the concepts are important, then having a huge family is not too good. So what is the minimal family? And then I'm just using this diagram here. I'm saying, well, this is L2, and this space S0 is inside, and S0 prime is outside. So this is a triple, simply a Banach-Gelfand triple in my terminology. You could say it's a rigid Hilbert space. In some sense, it's not as nice as maybe the situation with Sobolev spaces, where you have a Hilbert space sitting in the standard Hilbert space, sitting in the dual Hilbert space. Why? Because these are all reflexive spaces. I'm in a situation where, in my terminology, I would say this triple, thanks to Wilson basis, which are local Fourier basis, is isomorphic to the classical L2, L1, L infinity triple. So you can say, well, that's very easy. If you take the Wilson basis, orthonormal system for L2, just ask what are the absolutely convergent sums. And again, go back to this one here, that's A of t. When people do classical Fourier analysis, after a while they looked at the dual space of A of t. They called it the space of pseudo-measures, and they said it has distributional Fourier transform. I would say, yes, it's just going for the complete picture. Okay, but L1, L infinity are usually the troublemakers. They are not reflexive spaces or so. What can you do? Well, you add this. Here is also the problem. L2 is not dense in L infinity. You add the weak star topology. And I think that's maybe the insight of some papers I did over the years. If you do this, it helps so much. You get the density. And you can, for example, formulate the following statement. I just do it in words. The Fourier transform is a unitary Banach-Gelfand triple automorphism.
Don't you start topology is some relative distribution?
Yeah, it's a small version. I think I would say it's a poor man's version of distribution theory. Poor man's in the sense you do not need Lebesgue integration topological vector space or so, and I'm really working on this to present it in this way so that I can say, well, I can define this space as 0. It consists of Riemann integrable nice functions, continuous functions. It stands in all the LP spaces. Maybe I should say all the LP spaces are between those things. So you may give me an operator which is going from LP to LQ. I would say, oh yes, it's definitely mapping S0 into S0 prime. So S0, S0 prime. And then I have a kernel theorem and says, yes, it can be represented by a distribution, of course, now of R2D. And this kernel theorem is possible not with very much effort, despite the fact that clearly this is a infinite dimensional Banach space, therefore it cannot be a nuclear space, so there is no nuclearity or so. So I tried to come to an end. So the concept of Banach-Gelfand triples, especially this particular one, seems to be one of the most important consequences of all these studies, because it is both a useful tool for many things, from classical Fourier analysis to time frequency analysis to generalized stochastic processes we can describe in this way. And I think I'm working on presentations of doing it in a more general way. Now, it also has influenced my way of thinking about abstract harmonic analysis. And in one of the recent papers, I was trying to create something which is called conceptual harmonic analysis. And it's a bit like in the direction of Martin Vetterli's comments also. We are having continuous problems, but when we compute, we have discrete computations. Gabor analysis is a very nice field where you can say we can compute all the things in Gabor analysis over the cyclic groups or finite groups. No problem with convergence, and so everything can be realized in MATLAB. But the question is not, is Gabor analysis in the finite setting similar to Gabor analysis on the integers, similar to the one on the Euclidean spaces or the p-adic group or so? But the question is, can I use my MATLAB code to understand the continuous world? And there we have the question of, can you approximate discrete periodic signals, continuous functions by discrete periodic signals? And most engineers will say, yes, of course. I mean, sample long enough, fine enough, then you have more or less all the information that you need. And then it turns out, and it's one of my favorite comments, as 0 prime, the topology is just uniform convergence of spectrograms. Weak star convergence is the replacement of this uniform convergence concept to uniform over compact sets. So somebody, let's say an audio engineer, tells me he has a perfect recording of a piece of music. And I'm telling him, no, sorry, you're just doing a good weak star approximation, because there is all this infinite time, we're coming to the end, but you have just recorded 3 minutes. There's this infinite frequency domain, but you have just recorded from 0 to 20 kilohertz. So it's a tiny little rectangle. But yes, it's true, on this tiny little rectangle you have done an approximation within the numerical precision of MATLAB. So in a way, it has really a very good performance. And you see, again, our perception is coming into the game and so on. So having said these general things, I would like to just mention until 79, which was also the year of my habilitation, I was really working as a person in abstract harmonic analysis. I was interested in the applications or so, but with the advent of wavelet theory, the interaction really became much more intense and has influenced my work and, of course, allowed me to build up the NUHAC group in Vienna. This was because the problems were more concrete, they were more challenging. You could not just say, well, this is the problem. I mean, of course, we were choosing our problems, but you could not say, well, I replaced the problem by another one, but it was much more that you have to always come back to the question, what are the people wanting to do? So we had projects with Lavac and the engineers, with astronomy, with music. Monica Dörfler is doing this still. And so I want just to mention, if you're going to our webpage, the NUHAC webpage, database and tools, then you will find various things. In particular, you can have the last point I would like to mention, the talks, because if somebody wants to look up talks that I have given on the subject of Banach Gelfand triples, Coorbit spaces or so, there are many talks from NUHAC people, but also from other people who have done our conference. We provide, to some extent, MATLAB code, and so I think maybe it's a good point to stop here. Yeah, so this is how this looks like, how you can search for it, and I think I stop here. Thank you very much.